So in this problem, we have a crane pulling up a beam with a force equals to 28 plus 3s, being s, the distance that we go up, right? So the trajectory in vertical direction. And the beam has a mass of 2.5 megagrams. We are being asked to find the speed when it has risen 3 meters, so when it has gone up 3 meters. We learned that we could do the free body diagram of this problem, and then using the equation of motion, right, the Newton's second law, force equals mass times acceleration, we could find the acceleration, and since we are being asked to find the speed, we will have to integrate that acceleration. In this case, we will use the approach of the principle of work and energy, and we will relate the speed with the distance and the force. And also we need to find the time that it takes to cover that distance. So first of all, if I draw the free body diagram, just to see which forces are involved, I see that I have the force that is being pulled, right, which is given, and the weight. That's about it, because it's a rectilinear motion. So there is several ways to write the principle of work and energy. The way I like to write it is that the work done by non-conservative forces is equals to T2 plus V2, which is the total energy, kinetic energy plus potential energy, minus kinetic energy and potential energy in the first position, being this the first position and this the second position. Recall that there's different ways to write this expression, because you can calculate the potential energy as work done by the forces. For example, the only force that we have here, this is a conservative force. So we will calculate the work done by the weight as potential energy. So which are our non-conservative forces? The F. So let's start doing that. Oh, actually, the units of this, if you see the presentation, the units of this force are kilonewtons. Let me correct that. That the work done by the non-conservative forces, we will divide by the force, which will be equals. Definition of work is the integral from 0 to s of the force times the displacement, if it's exactly in the same direction, which is the case. So if we integrate that expression, we have 28 plus 3s squared ds, which is equals to, here we could put 3, but since we require to find the time, I will find a general expression for the velocity, and then I will substitute by 3. So the general expression for the work will be 28s plus 3s cubed over 3. In my limits of integration, so it stays like s. Okay, remember that this is in kilonewtons meters. So if I want to find joules, we will kilojoules, right? So we found this side of the equation. Now we have to find that side of the equation. Since it's at rest, the kinetic energy is 0, so rest. So this is initial rest, right? V1 is equals to 0.2 because it's the potential energy of the weight. And if I put my datum in the first position, datum over here, means that I have no height in my first position. So the kinetic energy in the second position will be 1/2 mass the velocity, and actually this is the velocity that I want to find. This is that speed that I'm being asked. And then I have the potential energy of the weight, which is mgh. Very important to recall the sign. So if my datum is over here, if I am going up, I'm gaining potential energy, so it's positive. So, and the height is s. So I can write mgs. If I substitute the numbers that I'm giving, mass is 2.5. Let me write it in kilograms. So therefore, I will be 10 to the third times 9.81 times s. So I have all the elements for my equation, so I will substitute and I get 28s plus s cubed. Since this is in kilonewton, let me put it in newtons. 10 to the third, and then that will be equals to T2, which is 1/2 mass times velocity plus V2, which is 2.5 10 to the third, 9.81 is. Since every single term of my equations is multiplied by 10 to the third, I'm going to cancel those out. And then I can solve for my velocity. And I get a general expression for my velocity. Right? That will be multiplied by 2 and divided by 2.5. I could actually add these two numbers. And since this is 28 minus this expression right here, I have the values right here. And actually multiply both terms for this factor. And I get an expression for the velocity, which is the square root of 2.78 s plus 0.s a cubed. And this is meters over second. This is a general expression for the velocity. So I could say that for s equal 3 meters, I just evaluate the velocity is equals to 5.47 meters over second. And that's the result that we were looking for. So this is this speed. Why did I find a general expression for the velocity? Because the velocity is changing respect to the position. So in order to find time, I have to integrate that expression, and I cannot integrate a constant because it will not give me the correct value. Since I started at rest and I take and I have a velocity at final, I have acceleration. So I cannot just integrate a constant. So to find time, I have to remember that the velocity, right? Velocity is the derivative of the position. So in this case, I will have velocity time equals dv. But as you see, the velocity is not given in terms of time. The velocity is given in terms of s. So if I plug out this in here, I will have s in this side of the equation, and t is my variable of integration. So therefore, I'm going to divide by the velocity. So I get here that the derivative of time will be equals to ds divided by this expression right here. Right? And I can integrate both sides of the equation. And now I can put the limit of integration, right? Because I want to know the time for that specific. This is an ugly integral. I don't expect you to do this integral, but your calculators can do it, the scientific calculations, or I just look up a solver on internet and online numerical integration program, and you can integrate that expression and get the time. So this side of the equation will be time minus 0, and integrating this expression and evaluating at 3 gives you 1.179 seconds. So I encourage you to look up an integration solver. So I'm going to write here, solve numerically. So I just wanted to make the same reflections that I did at the beginning. You could have found, using force equals mass and acceleration, the acceleration, integrate the acceleration and found that expression for the velocity, but we just used a different approach. And this approach of work and energy is used mostly when you want to relate speed and distance. So you don't have to go through the trouble of integrating the acceleration to get the velocity.